we're going to talk about and define resistivity. Here is a resistor, and we know that a resistor provides a resistance to current flow. But what is it about that resistor that determines the size of its resistance? Well, we know that a resistor provides a resistance to current flow by providing an obstacle to the flow of electrons. So if we have a longer resistor, we'll also have more obstacles for the electrons to bash into during their journey, and so the resistance, overall resistance, will go up. So as the length L of the wire that makes up the resistor, because a resistor is essentially just a wire or some other material which impedes the flow. If the length goes up, then the resistance will go up. If we have a higher cross-sectional area, so just first of all I'll just draw a short resistor versus a long resistor, and of course a resistor is actually a long piece of wire all curled up inside. So back to cross-sectional area, if we have a wire which has a small cross-sectional area compared to a wire that has a large cross-sectional area, more electrons per second will be able to flow through the larger cross-sectional area. So as the cross-sectional area goes up, the resistance will go down because more electrons can flow through that resistor. And the final thing that the resistance of a material depends on, the resistance of a resistor depends on, is its resistivity. And we give that the symbol ρ, and that's a property of the material itself. It can also be dependent on temperature. Now, as the resistivity of a material goes up, it's basically a property of that material. There are more obstacles in that material, maybe more densely packed, or the lattice of the material is such that the electrons find it difficult to flow through that. So for a material with a higher resistivity, you will find that the resistance will go up as well. Also, this temperature dependence, if the temperature of the material is higher, things are jiggling about inside, and so that will provide even more of an obstacle for electron flow. So as temperature goes up, the resistance will also go up. Just to put these into mathematical terms, for the length, we can say that the resistance is proportional to the length. For the cross-sectional area, we can say that the resistance is inversely proportional to the cross-sectional area. Of course, these things can be shown a little more thoroughly, a little more mathematically, but for now that's enough for us. And the resistivity, the resistance is proportional to the resistivity of the material. And when we combine those three things together, what we get is an equation which says the resistance is equals the resistivity times the length divided by the cross-sectional area. And if we rearrange that equation, we can say, just in terms of resistivity, is the resistance times the area on the length. And we can use that to determine what the units of resistivity are. It would, of course, be ohms times square meters on the top divided by meters on the bottom, which gives us ohm meters for the units of resistivity.